In chapter 43, we have seen about 180-degree mode of conduction in three-phase inverter. In this chapter, we will see about 120-degree mode of conduction. What does a three-phase inverter do? It converts DC to three-phase AC, where all the three phases are phase shifted by 120 degree. This is the circuit diagram of a three-phase full bridge inverter, which consists of 3 legs, 6 thyristors and 6 diodes, and the load is a star connected load. Three-phase inverter has two modes of operation, 180-degree mode and 120-degree mode. 180-degree mode, each thyristor will conduct for 180 degree and 3 devices will conduct at any time. So this has been discussed in chapter 43. Now we are going to see about 120-degree mode of conduction, in which each thyristor conducts for 120 degree and only 2 devices will conduct at any time. Let us see the conduction of devices in this mode of operation. We know each thyristor should conduct for 120 degree. Let us take A phase. In A phase there are 2 devices 1 and 4. So T1 conducts for 120 degree and T4 also should conduct for 120 degree. So but 1 and 4 are complementary devices. So there will be a phase difference of 180 degree between T1 and T4 conduction. So at 180 degree T4 will conduct and the conduction time or the period is 120 degrees. So what happens to this region? It is called a dead time or dead band, where none of the devices in A phase will conduct. Now let us consider B phase. You have 2 devices T3 and T6. We know A phase and B phase are phase shifted by 120 degree. So T3 should start conduction at 120 degree and the conduction period is again 120 degree. Again a dead band and T6 will conduct. Similarly, you can do it for C phase. So T5 starts at 240 degree and T2 it will conduct for 120 degree. So you have dead band here also. So you can see that at any time period only 2 devices are in conduction. So 6 1, 1, 2, 2, 3, 3, 4, 4, 5 and 5, 6. So there are 6 steps involved in achieving the output. So in step 1, we can see that 2 devices 6 and 1 are in conduction. So this is the equivalent circuit. So always a upper device and one lower device will be in conduction. So always voltage will be equal to Vs by 2, Vs by 2, because we have taken that this resistance is equal in all the phases. So for all the 6 steps, this is the equivalent circuit and this is the voltage. Only thing is device number will change. So if number changes, phase will change. So here 6 belongs to B phase. So it is connected here B, and 1 belongs to A phase. So write A here. So VA naught is equal to Vs by 2. VOB is Vs by 2. So VBO, if you find, it is minus Vs by 2. So this mode of operation is very easy. You can simply write the table for all the 6 steps. So in step 2, 2 devices 1 and 2 are in conduction. So 1 is the upper device connected to A phase and 2 is the lower device connected to C phase. So you write the formula directly. A naught and C naught you will get. Similarly, you can do it for step 3. So 2 belongs to C phase and it is the lower device, and 3 is upper device connected to B phase. So B phase and C phase voltage you will get. Similarly, you can do it for the remaining steps and directly fill up the table. So let us fill up the table for VA naught. So VA naught, you are getting this one. So what is VB naught? Simply phase shift by 120 degree. So this part should come here. So this should come here. So fill it up. And again for VC naught, it should start at 240. There will be a phase shift of 240 degrees. So fill it up. Okay. Now we will find what is VAB. So what is VAB? VA naught minus VB naught. So you subtract these two, you will get VS. You can do subtraction and you can find the values. So this minus this, you will get the VAB. Now how to find VBC? Again phase shift by 120 degree. So this one comes here, this one comes here. So phase shift it. Again for VCA, phase shift by 240 degree. Okay. So if you are not clear with this one, you can refer to 180 degree mode where I have clearly explained how to fill up the table. Now we will draw the phase voltage waveform. Again draw VA naught, phase shift this waveform by 120 degree. So your waveform starts here. Then again VC naught, phase shift by 240 degree. Now let us draw the line voltage waveform. Again phase shift by 120 degree and 240 degree to get VBC and VCA. Let us do the Fourier analysis for the phase voltage first. So this is the phase voltage waveform. You can see here that this is not an odd function, because if it is odd function, f of t should be equal to minus of f of minus t. So this portion should be here, but it is not symmetrical. Again, if you see half wave symmetry, it is not symmetrical. So we have to make this waveform symmetrical so that our Fourier coefficients will become 0. Now how to shift this one? Shift this one by 30 degree. Okay. So if you shift this one by this waveform by 30 degree, you will get this phase shifted waveform. So this S denotes phase shifted waveform. So you are simply shifting this one by 30 degree, and if you see the symmetry here, now you see this side and this side are symmetrical. So half wave symmetry is satisfied, and if you see this side also, you will get odd symmetry. So this waveform satisfies odd quarter wave symmetry. So if you see here, this side and this side remain same. So A naught and AN terms become 0 and only odd harmonics will be there. Even harmonics will become 0. Now let us find what is that Bn. Because An has become 0, you have to find Bn alone. What is the formula for Bn? This is the formula. Let us substitute it and find it out. So 2 divided by total time period. This is quarter wave symmetry. So we can take the time period as pi by 2. So 2 divided by pi by 2. And if you see this interval, so 0 to pi by 6, output is 0. So you can leave that. Pi by 6 to pi by 2, you have this voltage magnitude of Vs by 2. Okay, now integrate it. You can find that you are getting this term. So when n is odd, this term becomes 0. So simplify it, you will get Bn. Now you substitute the Fourier series Bn value, you will get this as the VAS. So if we see the voltage of VA naught, we have advanced the phase shifted waveform by 30 degree. So instead of omega t, you have to write omega t plus 30 degree. And B naught waveform will be displaced by 120 degree. So this 30 minus 120 will give you minus 90 degree. Again C naught will be whatever you have here, add plus 120 or minus 240. So you will get plus 150 degree. Now let us find the fundamental component. So what is fundamental component? When n is equal to 1, you will get the fundamental component. So what is the peak value? So this thing is the peak value of the fundamental component. So 2Vs by pi into cos pi by 6. How to find RMS value? Peak value divided by root 2 will give you RMS value. So let us find the RMS value of this phase voltage waveform. So the total time period is pi and the magnitude is Vs by 2. So square it, Vs square by 4. Simplify it, you will get the RMS value. Now let us find the total harmonic distortion, which will give you how much distortion is there in the output waveform. So percentage THT is equal to, you substitute these two directly, you will get 31%. This is surely less than the single phase inverter. Now let us do the analysis for line voltage. Let us do the Fourier analysis first. So this is the line voltage waveform VAB. We can see that there is no symmetry in this waveform. So we have to make it symmetrical so that we can eliminate some of the Fourier coefficients. So let me phase shift by 60 degree. So if I phase shift this waveform by 60 degree, so my waveform will become symmetrical. So you can check here, it satisfies half phase symmetry as well as it satisfies the odd function. So you can even check the quarter symmetry. So if you around pi by 2, if you check, you will satisfy quarter wave symmetry. So that A naught and An term becomes 0 and odd harmonics only will exist. Now let us find what is Bn. So Bn formula, substitute it. You can find that there are two intervals here. So let me take the time period as pi by 2. So t is equal to pi by 2. And in 0 to pi by 2, you have two intervals, 0 to pi by 3, you have magnitude of Vs by 2. And for pi by 3 to pi by 2, you have magnitude of Vs. So simplify this. You can find that triple n harmonics are 0, because if you put n equal to 3, 6, 9, 12, it becomes 0. So we call it as triple n harmonics are 0. And this cos n pi by 3 for other n values will be equal to 1 by 2. You substitute the remaining n values, it becomes equal to 1 by 2. So you can simplify Bn. So Bn is equal to 3 Vs by n pi. Now we will write VAB is equal to this Bn 3 Vs by n pi into sin n omega t plus, since we have delayed the function by 60 degree, you add plus 60 to this, because we have phase shifted the waveform. So now you add that 60 here. So BC will be phase shifted by 120 degree from this one, and CA will be phase shifted by 240 degree from this one. Now we will find the fundamental component. So fundamental component is 3Vs by pi, where n equal to 1, and RMS value is equal to this value divided by root 2. So let us find the RMS value of the line voltage. So you have to take for this interval 0 to pi. So you have three different voltage levels. So for first interval you have Vs, second interval Vs by 2 the whole square. So you will get Vs square plus 4, and again this you are squaring it, so negative value will become positive. So V minus Vs by 2 becomes Vs square by 4. So simplify this, you will get Vs by root 2. So Vrms and V naught 1 RMS we have found. So THT again you will get 31 percentage. An important point to be noted in 120 degree mode is that only two devices will conduct at any time. So two phases will carry the current, but the third phase will be always kept open. So if it is a resistive load, it is not a problem. That's why we consider a resistive load. Actually, if it is a reactive load, it may be difficult to find the potential at that point. So the points to remember here are: the three-phase inverter converts DC to three-phase AC output. In 120 degree mode of conduction, each thyristor conducts for 120 degree and two thyristors conduct at any time. And 6 steps are involved in achieving the three-phase output. And the THT of the output waveform is 31 percentage. So let us see the phase voltage and line voltage. So this is Fourier series expression for both the cases, and RMS value in both the cases, fundamental value, and if you find the THT, it will be same in both line voltage and phase voltage. If you want the study material, you can visit this website, and if you like the video, do subscribe to Read Electric Vehicle. Thank you.